Okay. So current density J, it's a vector quantity. Is the current per unit area normal to the area infinite. Now, if you've got a straight wire, then the current is moving along the wire, it's parallel to the axis of the wire. If you've got a bunch of varying voltages on a block of conductor, varying from point to point or varying in strength, then you get really complicated vector fields. Okay, and your current density represents the result of those vector fields. Okay, so the current density is a field that keeps changing in time. Right now, we're just learning about wires, but I want to give you the general definition. Okay, your book will tell you more. Okay. Well, you give the definition I gave you or last time. I'll make the statement this way and check my statements against what the text tells you. Conductivity is a current density per unit of potential gradient. Potential gradient on a wire is just change in potential per unit length, right? I'll say it this way, current density divided by the change in the potential per unit of length. And I'm not even sure I got the change of potential per unit of length, I'm pretty sure I did. So that would be like V over delta, V over L, right? And that's your current density and current per unit area. And resistivity So resistivity is potential gradient over current density. I.e. the reciprocal of conductivity. Okay. I'm going to give you a couple examples. I'm actually going to look them up. I'm just going to go here. Okay, so we just went online very quickly. I asked for resistivities, and first three things gave me definitions of resistivity, which is not an answer to the question of what are resistivities. Okay, but the fourth one actually gave me a table with resistivities. Okay, turns out silver is the highest from the table. It didn't list gold, but I think gold is a little higher than silver. Not sure. Copper and silver are pretty close together at around 6 times 10 to the 7th SI units. We'll figure out the SI units in a minute. Okay. And resistivity, well, it's going to be the reciprocal of that. And the reciprocal of 6 times 10 to the 7th is about 1.6 times 10 to the negative 8th. Again, in SI units. What are the SI units? Potential gradient is in volts per meter. Current density is in coulombs per square meter, right? That's current density, current per unit area. Oh, it's not coulomb, it's amps. Okay. So this equals voltage over amps times meters. Okay. Now, your voltage divided by your amps, is what you call resistance. Okay. And that has a unit that you call ohms. So your unit is ohms times meters. For ohms is your voltage divided by your current. Okay. Okay. So we had a little discussion, people questions about what does an ohm tell you and so forth. I pulled out a meter. We looked, you got ohms, you got voltage, you got amperage. Okay. Current. They're all related by this. Okay. So again, trying to explain this in perspective of this course. Okay. Let's go back to the situation we started. A thin wire in series with a couple of thick wires. Now, this could be a different material, like it could be tungsten, which you would use in an incandescent lamp. So this could be a big old wire coming into that little thin tungsten wire coiled up inside that lamp. Okay? Now, we're dealing mostly with LEDs or fluorescents these days. They're still incandescents around. Okay? So hopefully we've kind of taken a look inside an incandescent and see a little coil of very thin tungsten. Okay? Now, tungsten has a higher resistivity, a lower conductivity. Let's see what it is. It's about 30% of copper. So it's a pretty good conductor. Okay, you don't use to wire your house because it's really expensive. Because little tiny coils don't cost much. Okay. Okay, so what would you do with resistivity? Resistivity is what you multiply by, sorry, conductivity is what you multiply by your potential gradient to get your current density. Okay. And resistivity is what then you would divide into your potential gradient to get your current density, right? So it's a symbol for conductivity. Resistivity is rho. Conductivity is sigma. Okay. Don't use that one much. Symbol. Okay, so lowercase sigma, resistivity is, leave myself room to write a rho equals, I'm going to write it anyway. Rho equals potential gradient over current density. Okay, so in this situation, you multiply your current density by your potential gradient. Okay. Which means you multiply your current density by your conductivity by your electric field. And what do you get when you do that? You get your current density. And you just reason that out from the words here. Now, potential gradient is change of potential per unit of length, right? Current density is J that I defined up here, and sigma is your conductivity. Make sense? Just think through the words and what they're telling you. Alternatively, instead of sigma, you can use 1 over rho. Higher sigma gives you more current density for a given potential gradient, and low resistivity gives you greater current density per unit of potential gradient or per unit of electric field, because that's what potential gradient is. Okay? Makes sense? And I guess, just to be complete on the board, we note The potential gradient is the electric field. And it's change of potential per unit length. So here's potential gradient. Here's potential gradient. And here's potential gradient. Everything I've circled in blue is potential gradient. Now what I wrote in blue down here isn't, but okay, circled in blue. All the same thing. You want to be sure you kind of understand that at the deepest level you can. Okay. What's the current? You know, Jay, does that tell you what the current is? Okay, it took us a minute. Asking quite a bit, well, what's current density mean? So how are you going to get your current? Okay. If you know your current density, well, you're going to multiply it. And the current is a vector. It has a direction. It's measured in amps. And you're going to multiply that. You're going to multiply your current density by your cross-sectional area. And that should be no surprise in terms of the definition up here. You know, current density is current per unit area. If you know the current density, how do you get the current? You can multiply the current density by the unit area. Okay, so I think we're good here. And again, we're taking time to think through these things because these are important concepts. When you look at a circuit, think about a circuit, you want to be thinking about it at this level. Okay, well, I'm going to need some more board space. I'm going to pause for a second while I rearrange things. Voltage.
J right?
Well, there's no J
Ohms equal resistance.
in this expression, and we want to use this expression for and relate it to this. And you notice we got voltage here, right? Everything else here is part of resistance. So in terms of that expression, what is the resistance? Or if you want to start, what's the conductivity? Conductivity is what you multiply by voltage, right? to get your current density. But go ahead and think in terms of resistance. Algebraically, a little more complicated, but something to think about.
So let's pull out that section. That's one. Right. Yeah.
You know what? I have volts per meter here, which is a unit. Should be voltage over length. Hopefully I won't get it because I can't afford to lose brain cells. Okay, anyhow, we got IMV, right? I claim that we can get power. Now, over here, we derived this, and I think maybe I didn't have the camera on, so let's just quickly. Current voltage over resistance, so that's V over R, which is equal to this thing. So V over R equals this thing, where you got the L here instead of the M, right? I had volts per meter, which are the units of potential gradient. It was V over L in terms of a model. We get this equal to this, and we very quickly do the algebra, or just look at where things are. And we can realize that resistance is going to have a rho and an L in the numerator and an ACS in the denominator. And the voltage is going to divide out of the equation. So there's our resistance. The unit grows in ohm meters, as we saw earlier. Units ohm meters over meters squared, the ACS times L, which is meters, which reduces to just ohms. So there's your unit of resistance, answering the question of what's resistance. At least, what's ohms? Well, ohms is you measure resistance. And hopefully we've developed this in context that makes it give you a little deeper understanding. So the current is voltage divided by resistance then. And that's what we call Ohm's law. Okay, we'll come back to Ohm's law in a minute. But let's move on to the idea of power. If we know current and voltage, we can find power. Okay, because what does current mean and what does voltage mean? Think that one through. Okay, now it took a little too long to pull that out of you, but you got it, and that's okay. Okay. One problem in answering this question is you still got all this stuff in your head. So you're trying to answer this question in terms of cross-sectional areas and resistivities and so forth. All you need to know is what current measures and what voltage measures. Current is the rate at which charge passes a point. Okay, time rate. I'm going to say that a little more powerful language. It's a rate of charge transport. Okay. But in a wire, that just is the rate at which charge passes a point. Okay. The time rate. In other words, I is the derivative, or it's dq dt, where q is the amount of charge that is passed at this point. Okay. So you want to think about that. That's well worth thinking about. You're going to need it very shortly. Starts in amps, which is coulombs per second. And that's not hard to understand. You got charge flowing, you get that concept and so forth. Okay, and voltage. Is potential difference. Okay. In general, you get potential difference by integrating the electric field. That's not quite written right with respect to DS. It's with respect to S, but I'm just going to use DS here, violating the language just a little bit. Don't like to do that, but that should invoke the way we've set up integrals earlier. We have like a point charge and the potential difference between 2 points. Use the DR there because your position can be reduced to your distance from the point charge, okay? And using the fact that the electric field is conservative, okay? So you've got to have all that in your head to understand this well. So it's worth understanding that statement. So invoking the deeper understanding that should come from what we've done so far, we can understand voltage is joules per coulomb, which you can understand at a much lower level just by the symbols. But you want to relate it to everything else, In a wire, though, comes down to that. Well, as soon as we saw that currents in coulombs per second and voltage is in joules per coulomb, everybody knew that power was in units of work per unit of time, right? So it immediately follows the power is your current times your voltage. Again, understand that as deep as you can. Okay. So now, if we know given voltage and resistance, in other words, I've got a wire, I know its resistance, because I know its resistivity, because I know its cross-sectional area and its length, right? So I got a copper wire, I take a micrometer and measure its diameter, or maybe I know what the gauge is and I can convert that to diameter, okay? And I know how long it is, I can measure that with a meter stick, okay? So in that case, I can know R. I can look up the resistivity or conductivity, whichever I want, on a table. Most tables give you both. And I can multiply that resistivity by the length divided by the cross-sectional area. Very simple. Again, want to understand that as deep as you can. Okay. So if I know V and R, in any case, and that's a simple thing to do, I take a battery, 1.5 volt battery, put it across that wire. Well, you get internal resistance, which we'll talk about in a minute, but if you know the voltage across the wire, which you can measure, the voltmeter, that meter you got sitting there. how much power is being produced, or how much power is necessary to maintain that circuit. Okay, even though I put that in terms of a broad context, I got almost an instant answer, it'd be V squared over R. Okay, so yeah, well, power is current times voltage, right? In current, if I know V and R, I can get the current. So you cut right through all the stuff in the context that I gave you, and boom, got it. Now, make sure again you understand the whole context. As I heard you. The okay. And of course, if you know the voltage and the resistance, I'm sorry, the voltage and the current, well, you got that. If you know the current and the resistance, okay, then power is V times I is V over R. So how you put this and this together, you know, I'll make sure I did that right. That makes perfect sense because the more current you have, the more charge is transported. And over a given resistance, the more work it takes per unit of charge. So the current gives you a double dose, okay? Of that requires a double dose of power. It requires more power because you're getting more charge transport. And it also requires more power because it takes more work to transport the charge, okay? So again, you want to understand that as intuitively as possible. Okay. So that's a lot about what you need to know to analyze circuits. Now there's a little bit more. And we don't have time for a complete explanation, but if you have a circuit, okay, typically a circuit could be expressed like something like this. Okay, you've got a source here, some voltage. And you can think of the small terminal as pushing current. So current goes this way. And you've got two resistances, R1 and R2. Then the resistance is F. Okay. So and you can reason that out in terms of energy. We've got like 2 minutes left. I hope you over a couple minutes more than that. had that finger up. I wasn't sure if you're just trying to keep it out of your eye. Okay. I knew you'd want to keep it out of your eye. You might be asking a question. Okay. Now, if you have a situation like this, what you end up with is, okay, basic principle. Wires have zero resistance. It's not really true, but in a small circuit, it is pretty negligible, especially if you've got significant resistances here. There's not much current flow through the wires. Okay, so they don't affect the result of the circuit very much. If you've got long wires, like long transmission wires, that gets to be an issue. If you've got significant resistance over transmission wires, which means they got to do work to push the circuit, the current through those wires. And you've experienced that with trick of the generator. Now those wires are big and thick, but they're still really long. So there's a lot of resistance there. And you lose a lot of your power. Unless you get a superconducting wire, which is expensive. Okay. Not practical for long term, for long distance transfer power. Okay, anyhow, here, there's pretty much no resistance in the wire. So the voltage across this is the same as the voltage across this. Okay. There's a better way to. Your total resistance, the reciprocal of your total resistance is the sum of the reciprocals of your resistances. It's called a parallel circuit. That's a series circuit. Okay. You're going to see those symbols. I don't see where the problem are asking you a lot about parallel circuits, series circuits, although get into circuit electricity in another chapter. Okay. It was implicit that somebody made the correct statement. Your conclusion there is then I is V over R total. Okay, which should be V over 1 over R1 plus, sorry. V times I don't have room to do it. Our total in this case, we put all this over common denominator, right? 1 over R1 plus 1 over R2 is R1 got that back. Common denominator is R1, R2. So you multiply this by R2 over R2, this by R1 over R1, and you get R1 plus R2 over R1, R2. So the R total is the reciprocal of this, but I started to write out R1, R2 over R1 plus R2. That comes out that way. But you don't even bother to remember this because you might remember it backwards like I almost did. I've done that. Okay. Here's your basic relationship. And it's easy to derive this relationship, but we'll talk about that when we get into the next chapter. Since you asked, that's the way it comes out. You don't need that for let's do on Monday.